All right, folks, let's go ahead and let's get started. I hope, like I haven't seen anyone come by after school today to get that extra help. So, I hope you're able to get these videos and understand them and be able to work through them and be able to draw these diagrams and be able to understand how these molecular orbitals form when we are talking about these homonuclear diatomic molecules. And so essentially what we're doing is we're using very simple molecules to understand then how molecular orbitals work. And so what we need to be able to do, and this is what we did yesterday, is that we were able to pick any diatomic, homonuclear diatomic molecule. I'll mention heteronuclear diatomic molecules a little bit, hopefully today, but you should be able to take simple molecules such as this and be able to explain how these atoms bond together and how they bond together, how the electrons are shared between them, and then also the energetics of the electron of the different electrons in the molecule itself, and then finally be able to write out the electron configuration for the particular molecule. So we did lithium yesterday. So let's go ahead and let's take a look at this here. So lithium then, remember, has each lithium then has three electrons that we have to account for. We have to account for. Okay. We have to account for, so let's go ahead and write out the electron configuration for each one of these first. So for the lithium then, remember it's going to be 1s, 2, 2s1. For each lithium then, it's going to be 1s2, 2s1. And now make sure you keep in mind then that we're not, when we write out the electron configuration for this diatomic molecule. So we're looking at this particular molecule here, what the electron configuration will be. So this is the electron configuration for the atom, this atom of lithium. This is the electron configuration for this atom of lithium. And so we learned that, and we know that from first year chemistry. So each lithium atom has two electrons in the 1s orbital and one electron in the 2s orbital. So make sure you remember that. So these are the atomic electron configurations. These are the atomic, but we know that already. But what we're asking then is when these two lithium atoms get together to form this molecule here, okay, what would the electron configuration look like for the molecular lithium? Okay, so for the diatomic lithium molecule, what would the electron configuration look like? Well, first of all, we can't use S's and P's and D's and F's because all those are atomic orbitals. We learned back from when we talked about the hybridization that when atoms get together, they change these atomic orbitals into something different. That holds true for these molecular orbitals as well. When these two atoms get together, they no longer have S orbitals or P orbitals or D orbitals and so forth. They have orbitals that are formed that are different that we refer to as molecular orbitals. And so we learned then that when S orbitals get together, they will form then what are called these sigma, and they'll form two molecular orbitals. And so we saw then that these molecular orbitals were labeled sigma and sigma stars. Sigma meaning that this is going to be your bonding. Okay? And remember, we refer to it as sigma because remember, these two atomic orbitals get together, they will as waves, and they will line up in a manner in such that they will either be constructive or destructive. So constructive interference would give us then the sigma bonding interactions. Okay, this is sigma bonding. I'm sorry, sigma bonding molecular orbitals, and this is going to be your anti-bonding. So this is going to be your sigma anti-bonding molecular orbital. And again, sigma simply because of the way they line up. They line up in a linear manner. The two orbitals, the two molecular orbitals that form will line up in such a manner that we can draw a straight line through it. And so make sure you review Sunday's lecture in order to remember that. Okay. All right, so the two s orbitals get together, they form these two molecular orbitals. So these here represent the molecular orbitals, okay, that will be occupied now by these two electrons. And so the question is, why are we only looking at these two electrons here? Okay, why aren't we looking at all of the electrons? Well, remember, when we talk about bonding, only the valence electrons. Okay, so only the valence electrons, that is the electrons in the outermost energy level, will be considered. These core electrons here are not shared. So we have these core electrons here, which sit closer to the nucleus. They are not shared. And so therefore, when we write out these diagrams, when we draw these molecules, we only want to consider the valence electron. It's the valence electron. So that's why then we are only looking at the electrons in the 2s orbital here, and the 2s orbital here, and not looking at the 1s orbital. We're not considering all of them. So what actually bonds, what actually holds these two lithiums together is the sharing of this electron from the 2s orbital from this lithium, and this electron from the 2s orbital from this lithium. And so how are they shared? Well, when they come together and they form this molecular orbital, this molecule here, the two electrons then will drop down to the lowest energy molecular orbital. And this is, again, remember, this is when we write out the electron configurations for these molecules. The rules that we use are going to be exactly the same as the rules we use for atomic orbitals. We use the off-bound principle, we use Hund's rule, and we're going to use then the Pauli exclusion principle as well. Okay, so 2 electrons in the lowest energy level here. So this represents the lower of the 2. Remember, this is the pro-bonding state that we talked about. Okay, so this is the pro-bonding state. Why? Because this molecular orbital here is a lower energy state than even the atomic orbitals. And so when these two lithiums come together, okay, their valence electrons here will be at a certain energy level. They're going to come in, and then when they start to come together and they start to form these molecular orbitals, one of those molecular orbitals will actually be lower in energy than these 2s orbitals here. That's why we refer to this as a pro-bonding state, because what happens is that these electrons now have found a lower energy state, and they're going to sit in this lower energy state. And when they sit together in this lower energy state, this sharing here represents our covalent bond. So that is your covalent bond right there. The sharing of these two electrons, so therefore it'd be a single bond if you want to think about it in terms of a localized electron model, but there's the sharing of the 2 electrons between these 2 atoms here, and that gives us then our bond. Okay. All right, so with that said, then that's how the bond forms. Okay, and so when we write this out, we can write out the electron configuration for lithium in this manner here. Okay, so we don't want to consider the 1s. We're only considering the sigma, the bonding molecular orbitals, and so the electron configuration for the lithium molecule then is simply going to be sigma, and not the sigma star. Sigma formed from the 2s, not from the 1s. Okay, and convention sometimes will have you put a parentheses around it and a 2 here to represent then these 2 electrons. This is the orbital, so look at compared to the atomic electron configuration here. This is the molecular electron configuration for dilithium. This is the atomic electron configuration for lithium. So again, this number here represents then the primary energy level that we talked about. Okay, so this orbital here is found in this primary energy level. This is the atomic orbital that these 2 electrons are found in. Okay, so the way that we write down the molecular electron configuration is very similar to how we write down the atomic electron configuration. We indicate the orbital. Here, though, we indicate how this orbital formed. This orbital formed from the 2s orbitals, the atomic orbitals, and that there's 2 electrons in this particular molecular orbital. And so this is the electron configuration for dilithium. Okay, and so make sure then that you're able to do that. Okay, and so that's where we left off with yesterday. Okay, and so that's what we did yesterday. And so what I did was I asked you to do the electron configuration and write out the electron configuration for beryllium. Okay, let's go ahead then. Let's take a look at beryllium. Okay, let's quickly take a look at beryllium. Okay. So first of all, with beryllium then, let's write out the electron configuration for each beryllium atom. Okay, so for beryllium then, we have then the atomic electron configuration, 1s2, 2s2. So we're dealing with 4 total electrons. But again, we're only looking at this here. We're only going to look at these valence electrons right there. Okay? So we'll call this beryllium 1. And then let's go ahead and write this out. Then beryllium, each beryllium then is going to have 4 protons. 4 protons. Each one has 2 electrons in the first energy level and 2 electrons in the second energy level there. So same thing will hold true for the beryllium, the second beryllium. And we're looking at, so again, we're looking at 2 berylliums here because we're looking at diberyllium. So there's beryllium 2. It also has an atomic electron configuration of 1s2, 2s2. So it has its 4 protons here. Okay. in the nucleus, 2 electrons in the first energy level, 2 electrons in the second energy level. And I think if we draw it this way, you can clearly see then that it's going to be these 2 electrons that will be interacting with one another. So these 2 atoms will start coming towards one another. Okay, they will start moving towards one another, and they will form this diberyllium molecule. They will form, so from the atoms then, so let's make sure you understand, from these atoms, okay, so these are the separate atoms, okay, so this is an atom, and this is an atom, okay, and so from these separate atoms then, we're going to form a molecule, and I'm going to use the Lewis dot structure here to represent this. So we're going to have a molecule that has a set of electrons shared between it. Okay, so what we're doing is we want to examine this covalent bond right there. So how does that covalent bond form? First of all, does it form based on the molecular orbital theory? And so remember here, what we're going to do is this is going to be 2 electrons. So I'm going to draw it kind of as such, because we have 2 electrons here. So we have 1, 2, 3, 4. So we have a total of 4 electrons that will be shared. 4 electrons that will be shared between the 2 beryllium atoms, because you have 1 here, 1 here, 1 here, 1 here. Okay, so that's what we're going to look at. And so make sure you keep in mind that we have to account for 4 total electrons. Okay. All right, so what does this bond look like in terms of its energies? What does the bond look like? And let's take a look at that. Okay, so let's take a look at what would happen. Okay, so there we have it. Okay, so I'm going to draw it in here. So let's go ahead then and let's label what we have. And label what we have here. And so this is the 2s. So let's go ahead and I'm going to write this down really quickly, just so we can be. So this is going to be 1s2, 2s2, 2s2. Okay, so and then we also have here 1s2, 2s2. Okay, and so we're trying to see if this forms here. So these are the 2 electrons here. These are the 2 electrons here. Okay, so this one right here, real quick, folks. I want you to really quickly on your paper, just take about a couple seconds. What's this molecular orbital? How would we label this molecular orbital here? Take about 5 seconds. Write that on your paper. Okay, so this one here, then this is lower energy. This is our pro-bonding molecular orbital. So this must be then the sigma, and sigma formed from the 2s atomic orbitals. So this is going to be your sigma 2s, okay? So therefore this must be, so this is your sigma bonding. So this is your bonding molecular orbital. Okay, and so therefore this must be then your sigma star. This is then your, from the 2s, okay? This is your anti-bonding. Molecular orbital. Okay. All right. So hopefully you had written that down right there. Okay. Okay. So with that said, then, if this is the electron configuration for the beryllium atom, okay, what would be then the electron configuration for the beryllium-2? Okay. Now make sure you understand then, only 2 electrons can sit down here. Remember, only 2 electrons per orbital, and we had to count for 4. Remember, this has 4 electrons that are being shared, and we have to keep that in mind. So therefore, only 2 can fit down here. So as soon as this fills up, remember Hund's rule tells us that they'd have to spread out if they could, but if there's nowhere else for these, the remaining 2 to go, and so therefore they will advance to the higher energy level. So you can imagine 1 electron coming from here, 1 electron coming from here, and then another electron. The 3rd and the 4th can't fit into the bonding molecular orbital. The remaining 2 electrons, from each side here will have to advance up to the sigma star. Okay, all right. So the electron configuration for diberyllium, so the electron configuration for diberyllium, if we were to write that down, then would be then sigma 2s, and you would have 2 electrons there. Okay, and now unlike with lithium, okay, where we didn't have any here, okay, we would take a look at then at sigma 2s, so this can be our anti-bonding. Now we are forced to put 2 electrons in right there. Okay, this, we remember we said, is not an ideal situation. This is not an ideal situation. Molecules do not like to have electrons in a higher energy state unless they have to. And we'll talk about when they have to in just a moment. But if they don't have to, they don't like it here. Okay, and so with that said, then already this back here, suggesting that diberyllium may not be a molecule that actually exists. But if we go ahead and we calculate for the bond order, okay, let's go ahead, let's do one more check. Okay, for the bond order then, remember it's going to be the number of electrons that are bonding minus the number of electrons that are in anti-bonding. We divide that by 2. And so therefore the bond order here is going to be 0. Okay, so therefore if we take a look at this, folks, okay, two factors work against this actually forming. Okay, one, okay, so one, you have then a molecule in which you have electrons sitting in the anti-bonding state. And then 2, you have a bond order here of 0. Remember, the larger the bond order, the stronger the bond's going to be. This is 0. So that bond then would not exist. Okay, that bond, there's no strength in that bond there. Okay, and so make sure you keep that in mind. So does diberyllium exist? Based on the molecular, based on the analysis here of the electron configuration for diberyllium and the bond order for diberyllium, it doesn't exist. It does not exist. And so the question that I'm going to have for you then is that if that is the case, does the beryllium even exist as a molecule? Okay, and the answer there is no. Beryllium is going to be as a metal. Okay, so we know that beryllium exists, but it exists as a metal. And so much the same way that we saw with lithium, even though dilithium could exist, based on our analysis there, we know that lithium doesn't exist as a diatomic molecule. It exists as a collection of atoms together in which their electrons are being shared. The bond that actually holds lithium together is the metallic bond. The same thing holds true here for beryllium. The diberyllium does not exist. So we don't see diberyllium existing. We don't have that, but we do have beryllium as a, so it's not a covalent bond that forms, that holds these electrons together. It's a metallic bond that holds these atoms together to form then the beryllium metal. Okay, all right, so basically what we do then is we try to analyze and see whether a molecular, whether a covalent bond will form between two atoms or not. Okay, so we saw then with lithium, though it could exist, it doesn't because lithium is a metal, and so a metallic bond actually holds those atoms together. And with beryllium here, we see then that there's no covalent bond that could hold beryllium together based on our analysis here, but actually it's a metallic bond that holds these beryllium atoms together. All right, very good. Let's continue on then, and let's take a look then at what we have here. Okay, all right. So we talked about hydrogen. We talked about how dihydrogen could exist. We talked about how dihelium cannot exist. We talked about dilithium, okay, and we talked about diberyllium. Okay, so these are all atoms here. And these are all molecules then that are pretty simple. And what all of these have in common so far is that if you look at this is going to be, these two here are period 1, these are period 2 atoms here. These molecules form period 2. But what all these have in common is that all these atoms, all these molecules here, and the atoms that comprise them have electrons only in the s orbital. Okay, so we only have s electrons in the s orbitals for all of these atoms, for all these atoms. However, when we get to boron, which is the 5th element down, let's go ahead and take a look at boron really quickly. Okay, let's look at the electron configuration of boron. Boron is 1s2, 2s2, 2p1. So boron is the first element here that presents us with an electron in the p orbital here. So what happens when diboron forms? Okay, so let's go ahead and let's draw this structure here. Okay, so boron here, this particular boron then is going to have five protons. 5 protons in the nucleus. Okay, and then we're going to have 2 electrons in the 1s. That's what we have here, and we're going to have 3 electrons in the 2nd energy level. And so we're looking then, folks, make sure you keep in mind then that we are only going to look at the valence electrons. And so when this molecule forms, if it forms, it's going to form by these 3 electrons here being shared with a 2nd boron. Okay, and let's go ahead and draw the 2nd boron here. So P2, which is also 1s2, 2s2, 2p1. Okay, And so there you have your 5 protons in the nucleus, okay? 2 electrons in the first energy level, and you have your 1, 2, 3 electrons there. And so make sure you keep in mind then that when diboron does form, it's going to form as a result of the sharing. Okay? So when B2 does form, we have to account for 6 electrons that are being shared. Okay, so the bond that holds the two borons together in diboron is going to be the sharing of 6 electrons. Not quite what we refer to as a triple bond, because remember, a triple bond, and even though I used the Lewis dot structure in the previous one to describe diberyllium, this is not a triple bond. Remember, because these triple bonds, double bonds, and single bonds, these are localized electrons. But what we're saying here then is there are 6 electrons that will be shared. In these molecular orbitals, these 6 electrons will be shared between the 2 borons here that makes this molecule. And so the question that we need to answer then is, and I would like you to draw this out because I'm out of time right now, okay? As these 2 electrons get together, okay? As these 2 electrons together, how will the molecular orbitals form? We've only had to deal with the formation of the molecular orbitals from s orbitals here. Now the question then is, does the p orbital here change the way that the molecular orbitals will form, or the types of molecular orbitals that we will obtain? Okay? And the answer there is absolutely yes. Okay? And so what I'd like to do is I want to pick up with this discussion tomorrow. Okay? And we're gonna draw this diboron, and we're gonna see then how the number and types of molecular orbitals will change as a result of these p orbitals. Because remember, for the sigma bonding and sigma antibody molecular orbitals, that was a result of the s orbitals coming together. Okay? Here, we have s orbitals, but we also have p orbitals that have to be accounted for. And so how do the p orbitals, what type of molecular orbitals form from these p atomic orbitals? And so I'd like to go over that with you tomorrow. I know that this is stretching out a little bit further than we would like to. I'm going to speed things up a little bit tomorrow, okay? And then I want to wrap up with this discussion tomorrow so we can start talking about photoelectron spectroscopy. So please take a look at that section at the end of chapter 9 with photoelectron spectroscopy, and then we'll get started with that at that time. Okay. All right, very good, folks. I will see you tomorrow.